Okay. Yeah, so it is my pleasure to introduce Dana Bartosova from the University of Florida um, to talk about the topic on ultrafilters in set theory. So this is the third lecture on set theory, and ultrafilters is really a big thing in set theory. So it is my pleasure to have you, Dana, and please go ahead. It's all yours.
Thank you very much. Thank you for to those who made it. I'm sorry for the mess up with the day. You know, that's the highs of absent-mindedness to subtract the hours and not subtract the day. So I'm glad that some of you could make it, and for the other lectures, I am aware of it now. So as we heard, ultrafilters are big in set theory, and we can think about them as a set theoretic notion, but they are heavily applied in model theory. That's very standard tool. And also they can be applied in other places, among which, let me mention combinatorics, where you can even apply them to combinatorics of finite structures, even though they are inherently very infinite. So it's one of those places where you can solve something finite by going to something very large. So let's just start with where they come from. We often like to measure things. We like to measure distances. We like to weigh things. We want to know how big things are. And ultrafilter is such a notion of a measure of that is very rough. It just tells me whether a set is small or whether a set is big. So I like to be interactive. I know this is hard on Zoom and it's very late for you. So I'll be asking questions and I'll be happy if you answer, and please ask questions whenever as well. But I'll answer for you if you don't. So what do you think? What sets should be big and what sets should be small? Would it be natural if a finite set was big or even the empty set?
I mean, I know the answer. It's based on ultrafilter, based on the measure.
Right, exactly. So the ultrafilters, they have opinions about things, and different ultrafilters might have a different opinion about what is big and what is small. But typically we will be interested in those measures that are not big on finite, although we will have those as well. So that they will be special type of ultrafilters that you can think of as Dirac measures, the measures that are concentrated in one point. And we will be mostly interested in those that think that, that a finite set is small, as you have heard in set theory that the infinities, they never end. So somehow from that perspective, the finite sets look very small. And we will try to see some examples. So what is an ultrafilter? So there's two ways that I'm going to talk about them, but so somehow they're so predominant that people have different ways to talk about them. So an ultrafilter, let's think that it's a function that assigns to every subset of some set either 0 or 1. 0 for being small, 1 for being large, and we want two conditions to be satisfied. The first one says that if I have a large set and I have a bigger set, then the bigger set should also, as it's bigger by containment, should be big as from the viewpoint of the ultrafilter. And I also want that if I have two big sets, then they are going to intersect in a big set as well. Okay. And another way is that we can think of U as a collection of the big sets. So this is a choice. Of course, I could think about it as a collection of the small sets, but this is a dual notion. So we are thinking of the collection of big sets, which are here which are closed under supersets, right? This is the first condition up here. They are closed under intersection. This is supposed to be U. And there is this third condition that just corresponds to this U being a total function. So it says that it's always going to decide about a set whether it's large or not. And we cannot have, so this is something that we don't want, right? We don't want the empty set to be large. So we will exclude that on the next slide, but we will have that either A is large or X minus A is large, right? So we don't want the X to be small. So we want X typically to be 1, which is not necessarily the case if you leave it completely open, and we want the empty set to be small. And we will, from now on, consider only those. Okay, any questions? Okay, so ultrafilter just has an opinion about what's small and large modulo these two conditions. So what are some examples of ultrafilters? And it turns out that there's not that many that we can really describe in a pictorial way. So there are some that we can, and these are the ones that correspond to those direct measures, the ones that are concentrated in one point. So if I take an arbitrary element of my set and I look at all supersets of that, then this is definitely going to be an ultrafilter, right? Whenever I have a set and its complement, then X has to be in one of those spaces, and it's definitely closed under supersets and closed under intersection. So this is an ultrafilter. In a way, this is an ultrafilter that's not extremely important or extremely interesting because it just corresponds exactly to the point where it is centered. And we call them principal ultrafilters. And then we have the other ones, which are the non-principal ultrafilters. However, those are not really describable constructively because they cannot be proved in ZF, and we need a large portion of the axiom of choice, which is an axiom that's often used, but it's not constructive in nature. It's sort of something that looks very natural, but then when we apply it, it results in this object that we do not really know how to build. Somehow just falls down at us using this axiom. And as we said, we will exclude the empty set from being in the ultrafilter, because if we allow that, then we would have that the whole power set is an ultrafilter, and that is impractical. Of course, the power set of X, that's already object that we have, and it would tell us that every ultrafilter is contained in this maximum ultrafilter. We don't really want to make include the power set of X as an ultrafilter, so we will think that the empty set is not in an ultrafilter, is not large. Okay, so let's go into what does give us existence of some ultrafilters, non-principal ultrafilters, the interesting ones. So it turns out that without axiom of choice, we might have none. So it would not be a notion that is at all existent. And then we can have some ultrafilters without axiom of choice. So having ultrafilters does not apply axiom of choice, but it's not that easy to prove. Okay, so what is axiom of choice? Has any of you seen axiom of choice before? I have my student Jake who has to say yes.
Yes, yeah.
And do you think that axiom of choice should be always accepted?
No.
Okay, so here we go. So this is where set theory is on that boundary with philosophy, that we decide to accept some axioms as our building blocks for all mathematics, and you have seen them in the previous lectures. And this one is sort of kept separately. We have ZF, Zermelo-Fraenkel set theory, and then ZFC is with the axiom of choice, and that sometimes we have weaker versions of axiom of choice. So what does choice do? Choice gives us a choice function. So that is that if we have some collection of sets, then choice gives me a set that is going to pick from each of these sets one element. So in other words, it's going to give me a function that to each element in this collection going to assign some element of it. right? So I have this collection S, which are all of these sets, let's say A alpha, and to each of them, it's going to assign some member of it, right? When you, just to recall this notation, maybe that just means that I'm collecting all elements of the elements of S. So in here, it's taking the union of all of these A alphas. Okay, so anybody else has an opinion now about whether this is something that we should just think is true because it sounds so natural? What does Zuayo think?
I would take it.
Okay, yeah. Well, I'm pretty good with, well, I don't know what to do without it really, so that's more of that, but.
And you'll get 2 spheres out of 1 sphere.
Yes, isn't it great?
It's unnatural.
Well, that depends on our level of naturality, right? When we are thinking that some things should be preserved, then yeah. So there you go. That's why we have so many different universes in mathematics, because we have, I would say, reasonable contradicting opinions about what is natural. Excellent. But let's look at the finite axiom of choice. So if you have finitely many boxes, right, of balls, then every kid that's, of some reasonable age, say 4 and plus, can just go and pick from each of these boxes one ball and put them into a new box, right? And this is my selector. This is the result of the application of axiom of choice to a finite collection. And there, obviously that is actually a true statement. So the axiom of choice holds for finite collections. And this is just saying that if I have infinitely many boxes, then I can form another box, or I can fill another box with taking from each of these boxes one ball. But this is not provable from the other axioms of Zimmer-Fraenkel set theory. Okay, so axiom of choice itself is applied in many scenarios, but it also has equivalent formulations that may be applicable in different scenarios. Of course, one can prove that axiom of choice and Zorn's lemma are equivalent, so they are the same axiom, but they sound quite different and are suitable in different applications. So has everybody heard about Zorn's lemma before? At least the name.
I have.
Jake still owes me a proof of how axiom of choice implies Zorn's lemma.
Oh, right.
So it's actually easier or somewhat more standard to use Zorn's lemma to imply axiom of choice, but the other direction is also not bad. So actually the showing that they're equivalent, and if you have time at the end, then we can do that. Or we can do it next time. We have so many hours. So Zorn's lemma is about partial orders. And partial orders are a very general notion. Just whenever you are looking at any mathematical universe, you can usually equip it with some partial order. When you have any type of structures in algebra analysis, it often comes to a partial order or a pre-order. So it's a pretty general scenario. So if you have a partial order, that is, it's a relation, right? So this is a subset, it's a binary relation that tells me which element of P is less or equal than another element of P, and we want it to be reflexive. This is that the equality in there, right? So we want that P is less or equal than P. We want it to be anti-symmetric. That means that we don't cycle around. So if I have that P is less or equal than Q and Q is less or equal than P, then P is equal to Q. And then we want it to be transitive. So chains preserve that. So if I have P less or equal than Q and Q is less or equal than R, then also P is less or equal than R, right? Just making sure that we all remember what the partial order is. And we suppose that every chain has an upper bound. So what is a chain? It means it's a linear segment of this partial order, right? So any subset of P that is linearly ordered, that means that everything is related to everything. Then every such chain has an upper bound that is in P, right? So for every such a chain where every element is in P, there is an upper bound that is in P. And then the statement is that P has a maximal element. So maximal element for the whole P, that is some element such that it doesn't have anything above it, right? So if I were to find something above it, then I actually find out that it is equal to it. So there's those places. It's just to point out, we don't need to have just one. So there can be different ones, right? But above none of them is anything else. Okay, so we get that if every chain has an upper bound, then the poset has a maximal element. And let's just look at a few examples of partial orders so that we familiarize ourselves. So the usual linear order on natural numbers, that's a partial order. Okay, this would be a strict partial order. If I put here, then it would be the partial order as I stated it. Or we can look at the partial order, the power on the power set of X with inclusion. Or we can look at the divisibility relation on natural numbers. So I will say that n is related to m if m is a multiple of n. So just to check quickly, do the linear orders, natural numbers, or real numbers have maximal elements? Or do all chains have upper bounds?
No.
No, they don't, right? Because above every natural number, there is another natural number, in particular n+1. And actually for real numbers, we could use +1 as well, or many other things. So they don't have maximal elements. Do they have minimal elements?
Just the naturals too.
So naturals have a minimal element, and there, that's the element 0. Right? And it's actually a stronger notion than just being minimal. It's a unique minimal, and it's below every element. So it's a least element. Okay. Now, what about the power set? Does it have a largest element? I mean, does it have a, well, maximal element?
Yes.
And what is it?
The whole set.
Exactly. So X as a set is a subset of itself, so it's in there. So this is a maximal element. What if I take that out? So what if I look at all subsets that are not X itself? Do I still have maximal elements?
No.
Why is that? What would be so if I don't have maximal element, right, then for every element I have to find something that's larger in the poset. So what if I give you the element X without a singleton X for some X in X?
There would be nothing larger than it, but but X minus say Y would also.
Right, and that's exactly why I'm doing these examples. That's okay, because they are not comparable, right? If I have X is not equal to Y, then X without X is not a subset of X without Y, and vice versa, right? X without Y is not a subset of X without X, so they are incomparable, right? So then in that partial order, I have this X that's at the top of everything. I excluded it now, and now I have all these sets where I erase one element from X as maximal elements, and they are pairwise incomparable. There's no relationship in between them.
But if you have X minus X and Y, then that is comparable to both of those.
Right, and it's smaller than them, right, in the inclusion order. So it's
Yes.
okay, it's not larger.
It's not larger, but that means that both of those chains have a maximal element, but there is no single upper bound inside the set.
Inside which set? Right, so if I have any chain, then the chain is going to choose only one of them, right? It cannot choose, a chain cannot choose both X without X and X without Y.
No, you have two chains. You have X minus X,
Mhm,
which is greater than X minus X and Y. That's a
mhm,
chain.
that's fine.
And you have X minus Y
Mhm,
and X minus X and Y. That's the second chain.
correct.
Okay, they both have a maximal element.
Mhm,
Okay, but there's no upper bound.
that's correct. So that's the difference between maximal and the largest element, right? They are incomparable. They are maximal, means there is nothing in the process that's larger than that.
They're the top two, the two upper bound, no, excuse me, the two maximal elements are not comparable, correct?
That's
But
fine. Mhm.
the set itself doesn't have an upper bound.
Which set?
The X mine
X minus X and X minus Y?
right, because you don't have X itself in the set.
That's correct, but that's the thing, that's not a chain, right? And we only need upper bounds for chains in the statement of Zorn's lemma.
I thought it said it the chain had to have a maximal element.
Right, but this is not a chain, right? So
You have two chains, each have a
Yes.
maximal element.
that's fine.
Okay,
So you have two maximal elements.
right, you have two maximal elements, okay, and no upper bound. You could consider the sets comprise of the elements P, R, S, where P is less than R and P is less than S,
Mhm.
and R and S are not comparable. Same thing,
Yeah.
just three elements. You have two chains,
Mhm,
and each chain has a maximum element, and
mhm.
but there's no upper bound in the set for
Yes.
all chains.
But which chain doesn't have an upper bound? So it's about one chain having an upper bound, right? So you gave me two chains.
Not all chains having an upper bound.
Yes. Every
Okay,
chain has
okay.
an upper bound. Great. Thank you so much, because these things are very important to clarify. Excellent. So let's maybe leave the division, because I'm sure that you can figure it out. It's a nice poset as well. Partially ordered sets, we call them posets often. Okay. So this is great because we will be using Zorn's lemma. So we are now clear on what the statement is. So now let's go to where we do get ultrafilters from, and where we do get a lot of them if we do have axiom of choice. And if we take away the last condition from an ultrafilter, the condition that makes it ultra, meaning that it has an opinion about every single set, whether it's small or large, then we get a notion of a filter. So it's a partial ultrafilter in a way, and it satisfies the first two conditions. That is that if I have something in a filter, so the filter thinks it's large, then a superset is going to think the same, or it's going, the filter is going to think the same about a superset. And again, closure under intersections. So we have that if A, B are F large, then also the intersection is. And filters, the not being ultra gives us more filters to construct. So there's actually a number of filters that you can just say these are going to be the elements of the filters, or at least specify a filter base. That is that you specify the elements that are going to be in there and close under supersets. So I start with a filter that's very present in mathematics, and you might have even used it implicitly at high school. And it's called a Fresha filter. So the Fresha filter consists of cofinite sets. So if I have any infinite set, then I can look at throw away a finite set, and whatever is left is cofinite. And this is a filter. This is definitely closed under supersets. And if I have two cofinite sets, and their intersection is also cofinite because their complement is going to be the union of the finite sets that I excluded, and this is still finite. Or I can think of the filter that is generated by arithmetic progressions and natural numbers that contain zero. So here I should really say generated by. And here I mean the smallest filter that contains it, and here is going to be the filter that contains all supersets of these arithmetic progressions. We will be talking about arithmetic progressions next time, so let me just briefly remind you what they are. Arithmetic progression is anything that starts at some point of natural numbers, and it's all multiples. It's all multiples of some natural number shifted by this d. And now when I'm looking at the ones that contain zero, then this a is going to be zero, right? So they are all just multiples of some n. In other words, they are the group nz, subgroup of, sorry, semigroup, submonoid. Okay. So back to the Fresha filter, where you might have seen it before, is in convergence of, say, real numbers. So we know the definition of convergence, right? We have that a sequence of real numbers indexed by natural numbers converges to some point R if, whenever I choose some neighborhood of it, that is some epsilon neighborhood of R, then the indices, when I collect the indices of the Rn's that fit into this neighborhood, then this is going to be a cofinite set, right? We say that for all but finitely many of these Rn's, they are in the epsilon neighborhood. So in other words, we are saying that the indices of Rn's that are in the neighborhood, they have to be in this Fresha filter. Okay. So now we said that the principal ultrafilters were the ones that concentrated on a singleton, on a finite set, therefore. And Fresha filter tell me that all finite sets have to be small because it chooses that cofinite sets are large. So now if I get any ultrafilter to contain the Fresha filter, which we say extend, then this is going to be non-principal, right? So if I'm able to extend filters to ultrafilters, then I will be able to get non-principal ultrafilters. And ultrafilters, when we excluded the power set of X, they are actually just maximal filters, right? So we still sort of silently slated zero is not. Yeah. Okay, so let's talk more about the notion of how we compare filters, right? Because I'm saying maximal, what is the post set and how do we deal with that? And that's bringing us to the use of axiom of choice. Any questions, any doubts? Okay. So how do we extend filters? So it turns out that under the axiom of choice, and in particular the application of Zorn's lemma, every filter that we have can be extended to an ultrafilter. So in particular, if I start with an infinite set, that extending the Fresha filter will give me non-principal ultrafilters. Okay, so what is the post set that we are going to consider? It's going to be all the possible adapts for being an ultrafilter. So we are going to look at all possible extensions of my filter F into some G, where G is also a filter. And then we will show that if I get a maximal element of this partially ordered set, then this is going to be an ultrafilter that contains F. So this is a partially ordered set of sets, and it's just ordered by inclusion, right? So we are looking at subsets of the power set of X. So suppose that we have some chain in P. That means that I have my filter F, and then I can extend it by these G's. And I want to show that there is an upper bound. Well, this is a common common phenomenon when we can apply Zorn's lemma to some partially ordered set of sets, that the union of the chain is going to be an upper bound, right? So let's maybe stop there for a moment. So why is the union of filters still going to be a filter? Right, it's definitely going to be closed under supersets, right? Because if I have any set in the union, it came there with some filter, and therefore all the supersets were already in that filter. And if I have two elements that I have to check the intersection property for, right? So I have some AB inside of here, then those came from somewhere in the chain. So there exists some G and H that are in the chain such that you know, A is in G, B is in H, but then we have that, let's say without loss of generality, G is smaller than H, right? We have a chain, so one has to be contained in the other. Well, then I get that actually A and B are both in H, and therefore A intersection B is in H because H was a filter, right? So this is often used also in algebra to find some maximal elements like maximal ideals, because we are checking something that is finitary, therefore we can find a witness in the chain that includes all the elements that we are interested in. Okay, so by Zorn's lemma, the poset P has a maximal element, let's call it M. So this is some filter that extends F. This is just by definition of being in P. And we just need to show that this is ultra. So we just need to show that for every subset, there is either the set contained in M or the complement is in M, right? So for A not to be in M, we need to know that if I add A to M, right, then this is not going to give me a larger filter, right? Because that would contradict maximality of M. So if M union of, if A is not in M, that means that adding A in breaks down being a filter. And the only way that we can break that, we cannot break the superset thing, right? We can always close under supersets. So that means that at some element of B, A is going to give me empty intersection with B, right? But then if that happens, then I will have that B is included in the complement of X. And therefore we have that X being X minus A is a superset of B, and therefore it has to be in M as well. So under AC, every single filter can be extended to an ultrafilter, and you can try to build some filters by yourself. Of course, we are interested in the ones that extend the Fresha filter, so only consisting of infinite sets. And that already gives us that there must be many ultrafilters. Any questions? Okay, so let's just go a little bit into how many there are. This is going to be without proof, but it is an old result. And it says that there are going to be actually as many as it's even possible. So let's remind ourselves a little bit of cardinals from your first lectures. Remember that the cardinality of natural numbers was the smallest infinite cardinality, which we denote by Aleph naught. And then we know the Cantor's diagonal argument that if we look at the power set of natural numbers, then this is going to be a cardinal that is greater than Aleph naught. And in finite sets, we know that the power set of some set of size n has size 2 to the n. So to extend the cardinal arithmetics accordingly to how it works in finite world, we also have the definition of the exponential to be exactly that. So we have that the power set of natural numbers is the cardinal that we denote by 2 to aleph naught, and we know this is larger than aleph naught, and that's how we can get larger and larger cardinal numbers and never stop. So now this is true for arbitrary cardinality. So if I have any x, finite or infinite, right, then the power set of x is going to be the cardinal 2 to kappa, and it's going to always be strictly greater than kappa. So under axiom of choice, Pospisil showed that there are 2 to 2 to kappa ultrafilters on a set of size kappa. Well, for any infinite cardinal kappa, because on finite set we only have the principal ultrafilters, and therefore there would be only kappa many of them. So this here the infinite is important. And I'm saying that this is as many as there can possibly be. Well, this is because of where the ultrafilters come from. They are sets of subsets of x, right? So they live in here. And if x is of cardinality kappa, then the power set of x is of cardinality 2 to the kappa, and then the power set of x is 2 to the kappa. So I cannot possibly have more ultrafilters than in the number of elements in this double power set. Okay, so there's the big contrast between the axiom of choice, where we have as many ultrafilters than you could possibly hope for, and without axiom of choice, where you might not have any ultrafilters, and then we have a whole world in between. Okay, so ultrafilters are interesting for set theorists for many reasons, but one of them is that you can define reasonable properties of an ultrafilter, and it may or may not exist. So what does that mean? Like you had independence of both the continuum hypothesis and the negation of continuum hypothesis with the axioms of set theory. You can also have other independence results, like whether an ultrafilter with a certain property exists or not. And they have some combinatorial properties as well that are interesting to study. So there is a bunch of them. If you're interested in that to look up, and P points that I chose here are about the oldest ones and the easiest to demonstrate it. So we will be using CH to construct these P points, and then we will mention that without CH, we might not have any in our universe. So recall that CH tells us that every finite subset of real numbers has either size aleph naught or 2 to the aleph naught, right? So this was the size of natural numbers, and this was the size of real numbers, right? So it says that all the sets are countable, or if they're uncountable, they're already of the same cardinality as the set of real numbers. In other words, 2 to aleph naught is the cardinal that's right after the cardinality of aleph naught, right? So we get that there are, we can define the cardinals to just keep going. So we have the smallest infinite cardinality, which is smaller than the second smallest infinite cardinality, and so on. And the continuum hypothesis tells us that aleph 1 is equal to 2 to aleph naught. There is nothing in between aleph naught and 2 to aleph naught. And you have seen that you have models of that theory where you can get as many things as you want in between. So we will from now on denote the set of ultrafilters by beta n, so that we have a shorter way to talk about it. And this is not a coincidence. Beta stands in general for the checksum compactification of spaces. And it is indeed the case for discrete spaces. So we will talk about the topology more later on. And we introduced this partial order on subsets of n, which is relevant to ultrafilters, to filters and ultrafilters, which is an almost containment. So we will say that A is almost contained in B if, oh, sorry, this is supposed to be the other way around, right? So A is almost contained inside of B. That means that it is contained in B modulo a finite set. So what is sticking out of B in A is finite. So when we are thinking about non-principal ultrafilters, right, they can only have finite sets, infinite sets in there. And therefore, when I have two elements in there, then their intersection cannot be finite. So somehow this is going to be negligible from their viewpoint. And a P point is now going to be an ultrafilter such that if I have any, oh, okay, so this was supposed to be, I'm sorry. Is it? No, this is correct in countable. Yeah, okay, I am in beta n. Okay, this is good. This is all right. No. I need this to be more general. I'm sorry. If I have any, sorry about that. Jake, have you started studying P points yet?
No.
Okay, so topologically, we want that every collection of neighborhoods has, so P is the largest. Okay, yeah, we want that for any subset. Yeah, no, this is fine, I think. Let me see. Okay. I'm sorry, I'm blanking out now. I think I need something stronger, but I don't want to make it too strong. Let's see. Okay, as we are getting to the 9:50 mark, let's take about 8 minutes break to 9:55, and I'm gonna come back to you with the answer when my brain. I must admit that because of the mess up in time, I was making these slides until 5 a.m. So my brain is a little, no, that's okay. I just have a little crazy time right now and I'm enjoying this, but I'll be back in 8 minutes, okay?
Right, sure. So let's take a break. And I think, what time do you want to meet again? In about, did you say 10 minutes?
8 minutes.
8 minutes?
Yeah, we can do 9:55.
Okay,
fine.
so 9:55 then.
So
right.
Whatever it means for you, 55 should be the same, right?
That's right, yes.
Okay, I'll
All
just hang here, right? Okay. All right, we can start back whenever you guys are ready.
Whenever.
Okay, it's all correct. I was just overly cautious. Okay, so a p point means that whenever I have a sequence, so this is on natural numbers. If you had a large set, then we would have to have a larger cardinality, but we are on a set that's countable. So for any sequence of sets inside of the ultrafilter, there is some set inside of the ultrafilter that is almost contained in all of them. We call this P a pseudo intersection because it is not quite an intersection, but it sticks out of each of these sets at most by a finite set. Okay, so every principal ultrafilter is obviously a p point, right? Because the singleton that contains X is always going to be inside of any sequence of elements of the ultrafilter. But otherwise, it's actually impossible to prove from even out of ZFC that p points exist. But the proof that they may exist was first, and that was all the way back to Rudin, but Walter Rudin, not Mary Ellen in this case, which says that under CH, there is a non-principal p point in beta n, right? So the principal ones are obvious, so we have to exclude them to have a theorem. And let's just recall what is the CH, what is CH going to give us, right? We're going to use that 2 to aleph naught, so all subsets of the powers of n, they have cardinality aleph 1, which is the cardinality of the first uncountable ordinal. So cardinality is shared by many ordinals. So we are going to choose the first uncountable ordinal, somewhat as a representative of that cardinality. And the big advantage of that is that if I take any smaller ordinal, then the size of that ordinal will still be aleph naught because I'm choosing the smallest ordinal that has cardinality aleph 1, right? So maybe just to recall what ordinals were, these are continuation of natural numbers. So as we climb the ladder from 0 to 1 to 2 and so on, then when we collect all of them, then we get the first infinite ordinal number, which is the set of all natural numbers. And then we have omega plus 1, which we think of as omega union singleton omega. And then we have many of them that have the same cardinality until we arrive at the omega 1. And this is where we are. So anything that's below it has a bijection with omega. Okay, so we use the CH to enumerate the power set of X in the order type omega 1, which is now the cardinality of the power set of X. So we just say they're going to be in arbitrary way A alpha or alpha in omega 1. And we are going to build the infinite sets that are going to generate our ultrafilter. And again, we have enough of them as per cardinality, and we will assure that for each A alpha, they will decide whether A alpha or its complement are going to be in the ultrafilter or in the filter generated by B alpha, and therefore it will be an ultrafilter. So what do we want? We want them to be ordered by this almost inclusion. So we want to always make sure that we are only sticking out by a finite piece. And we want that we are deciding about every set. So we are going to say that for every alpha, when I consider this A alpha, there is going to be some beta such that this B beta is going to capture whether A alpha will be in the ultrafilter generated or filter generated by these B betas or its complement. And then we are going to let U to be all these be the filter that's generated by these B alphas. Okay. So by this first property, we get that the U is going to be P filter, right? Because now if I have any countable sequence, then it's going to, each of the elements is going to have something in this sequence B alpha that is almost contained in it, and then I can find some further B beta or B gamma that is going to be inside of all of them, and then the second condition gives me the ultra. So on the next slide, we are going to construct these this almost descending sequence. Any questions about the idea of the proof? Okay, so we have px enumerated, and we are going to construct this chain, almost chain. So this is the part that we had on the previous slide, and now we are gonna build it. So we just start with the whole set X. You can't really spoil anything there. Okay, I'm sorry, this was natural numbers. And we are gonna proceed by transfinite induction over all the ordinals alpha that are smaller than omega 1. And recall that we have two types of ordinals, right? We have the ordinals that are successor ordinals, right? So we have omega plus 1 is a successor ordinal because between omega and omega plus 1 there is nothing in between. And then we have limit ordinals, right? So for instance, omega to omega would be a limit ordinal. Okay, so now let's look at the successor step. So suppose that we have constructed B alpha, and we want to construct B alpha plus 1, and we are going to consider my B alpha that I have, right? And recall that I know that what I have constructed so far up to alpha is in that almost containment. So I basically only have to worry about the intersection with B alpha of my thing that I want to take care of, right? So I want to take care of at step alpha of the set A alpha and decide whether A alpha or n minus A alpha will be a superset of the B alpha plus 1. And now, well, what do I have? I have an infinite set, right? All of these B alphas are infinite. And then I have the set of all natural numbers that I split into two parts. Let's say that this is one part and this is the second part. Well, then at least one of these parts has to intersect this infinite set in an infinite set, right? Otherwise the set would have been finite. So if the intersection of B alpha with A alpha is infinite, then we are going to throw it in as the B alpha plus 1, or otherwise we are going to look at B alpha intersection n minus A alpha. Of course, they both can be infinite, but at least one of them is. Okay, so now we consider the case when alpha is a limit ordinal, but it is still going to be countable because it's an ordinal that is smaller than aleph naught. So we can enumerate all of the sets that happened before in the order type of natural numbers, right? Or we could put omega here, whatever is your favorite choice, right? So we can find a bijection, right, between the numberings. So now we are going to use the order type of omega to find this A alpha, sorry, B alpha. I'm so sorry. What I wanted really, that's exactly what I'm saying, B alpha. So of course true about A alpha as well, but that wouldn't be really what we want. So now we are going to consider all of these BNs, and we know that they are all infinite, so we can do the following, that for each n we are going to choose some element from this Bn that is going to be different than the ones that we had chosen before, and then we are going to collect all of these inside, and then this is going to stick out at most by finitely many things from each of these BNs, because when I look at what it sticks by out, it's only coming from the previous numbers. So this is the trick. So how we use the continuum hypothesis, we use the continuum hypothesis by being, well, I can demonstrate it here, by being able to enumerate the power set. And then whenever we have something that we are still building in, right, anything that we ever consider is actually just countable. And therefore, I can do whatever inductive process without having limit points. So a little bit of magics, but if we proceed to treat infinity and infinite numbers in the way that we have chosen and that you have been introduced to, then this is the result. Any questions? Okay, so we know now that p-points may exist, but it doesn't say that they do not exist necessarily, because if we add some axiom, maybe that axiom was redundant. Maybe we didn't really need that enumeration. And Schillach quite a bit later proved that it's with proper forcing, that it is consistent with ZFC that there are no p-points. And somehow that proof is a lot more complicated because what Rudin had to do, he had to construct one p-point, whereas what Schillach needs to do, he needs to kill all p-points, right? So anything that could be a p-point in his model, he has to get rid of it being a p-point by making sure that in the extension there is going to be some sequence that does not have the pseudo intersection, but then in that new model might introduce other p-points, so he has to take care of them all. Okay, so now I would like to move on to the topological part. So this can be done for ultrafilters on any discrete set, any set that we have talked about. But let's focus on natural numbers because it's already very interesting in there, and it's just somewhat easier to imagine. And also, next time I would like to talk to some number theoretic applications, and then we will be looking at this space also over natural numbers. So now the space of all ultrafilters on natural numbers can be equated with a topology, and this topology is very beautiful. It's generated by open sets, closed sets, that is sets that are closed and open at the same time, which come from arbitrary subset of A, and it collects all those ultrafilters in all those ultrafilters that contain this set. Right? So you can also think about it that a closure is the filter that's generated by A, that is all supersets of A, and this neighborhood is going to be all ultrafilters that contain this filter, and we will talk about this just now. Okay, just one question. Everybody's comfortable with topology, open sets, closed sets?
Yes, for me.
Okay. Well, it's better not to be silent in these moments because I can quickly recap something. I will be recapping a lot, so just stop me anytime. Okay. So now this is a basis of open sets. Well, let's just maybe quickly say why it is. If I say that it's open, then its complement is also open, and therefore it's clopen. So, well, if I look at N without A, then these are all ultrafilters that contain the complement. But we have that every ultrafilter contains either A or its complement. So we get that this is actually all of beta N, right? So if I say that A bar is an open set, then just by definition, I get that the complement is also an open set. And therefore, it has to be also closed. Both of them are closed, right? So it's yeah, we generate the topology. What does that mean? Well, that means that every open set is union of these, but also it's a topology for closed sets, right? Because if I have a basis for open sets, the complements are a basis for closed sets. But here, if I take complements, I get exactly the same collection of sets. So it means that every closed subset of beta N is an intersection of some collection of these sets, right? So every closed set is determined by some collection of subsets of N. But what does that really mean? Well, if we look at what these guys are, right? These are all ultrafilters that contain A alpha. So if I look at this intersection, then I'm gonna get all ultrafilters that contain A alpha for each element of this set, right? So now if I have that right. So now I get that the sets that I started with, the A alphas, I can collect them into a filter, right? So as long as the finitely many elements of these A alpha, so if I have, okay, if it's non-empty, if C is non-empty, then this is going to be a filter because it's not going to contain empty set. So now, basically, when I collect all of these A alpha, there's a base for a filter. That means that if I take all B's that are supersets of some A alpha, this is a filter. And now we are going to say that this is the filter that corresponds to C. So we have a duality between the closed subsets of beta n and filters on n. And we can heavily use that. Any questions? So we have some topological space, but what sort of properties does this topological space has? So this space is Hausdorff. So let me recall what Hausdorff means. Hausdorff means that when I take two elements, x and y, then I can separate them. I can find some open set around x and some open set around y such that their intersection is the empty set. So how do I do that in the checkstone compactification? Well, I can take two ultrafilters. Well, if they're not the same, that means that they cannot be the same collection of sets. That means that there is some A that is in U that is not in V because they are different, but then that means that n minus A is in V. Right? But then we get these neighborhoods A bar of U and the neighborhood n minus A bar of V that are disjoint, right? No ultrafilter can contain both because we bend empty sets to be in an ultrafilter, and they are both open. So, okay, easy enough. Now, it is actually a compact space, and compact spaces are especially beautiful because they have this finiteness in there. So what does it mean for a space to be compact? It means that every open cover, so cover of by open set, so every element of O is open and the union is X, has a finite subcover. So there is a finite subfamily of O that covers all of X, right? And maybe let me mention some examples. Does anybody know an example of a compact space?
Any finite space.
S1.
Yes, so finite spaces, and among discrete spaces, these are the only ones, right? Once you have an infinite, then every element is open, and then you cannot get that, right? Then we get the interval 0, 1, right? This is compact, and more generally, every closed bounded subset of a Euclidean space of any finite dimension is compact. So we get, this to any cardinality, and it actually turns out by Tikhonov's theorem that if you take any compact space and you take it to any power, then this is still going to be compact. So we can have very large compact spaces, and in that vein, as we have finite space being compact, we can take 0, 1 to n. This is going to be compact, and this is the Cantor space. And so, then of course, this is 4, but it's really 3 in this guise, right? And then we can just maybe remind some of the typical spaces that we have. We can have the two-dimensional torus, the donut, right? Or we can have spheres, These are in the Euclidean spaces, but to have something very concrete. So these are, yeah, I'm sure, spaces that you have seen. But this space is going to be a lot larger in a sense that will be on the next slide. And because of this non-constructability of non-principal ultrafilters, it's not so easy to pin down how it looks like, but we have studied it a lot and have a lot of information. So compactness has a dual version, or the definition has a dual version, which is immediate, right? So where does it come from? So I have my X, and I was looking at covers by open sets. So I can take complements of these covers, and then I get some closed sets. So these are my C alphas, are these closed sets. And if I have that, C alpha is equal to O alpha, where O alphas, they form my O, right? So it's, sorry, this is the complement. That's what I wanted to say. C alpha, this way, and this is the complement of these O alphas. So now if I say that O covers the whole thing, right? That means that the intersection, all of these C alpha for alpha in I, is the empty set, right? And then it means, what does it imply? Is that, well, there was a finite subcover. That means that there exists a finite subset of I such that the intersection is already empty. Okay. So now this equivalent version of compactness is a contrapositive of that. That means that if for every finite subset, I do get that the intersection of these C alphas is non-empty, then the intersection of all of them is non-empty as well, right? So this is what it says here. So it's a contrapositive of what I have just written here, therefore it is equivalent, right? So if I have an empty intersection of a family of closed sets, then this is witnessed by some finite subfamily. So in other words, we have that if the family satisfies what's called the finite intersection property, that is that for every finite piece of I, the intersection is non-empty, then the intersection of all of them is also non-empty, right? So think about it maybe in the unit interval, right? If I have, let's say, closed subintervals, right? Then the intersection is going to be non-empty. This is not the case when I look at the open interval 0, 1, right? Because if I look at the sets 0 to 1 over n, right? These are relatively closed in 0, 1 because they come from a closed set in real numbers intersected 0, 1. And then I'm going to just go with n to infinity. Then this has the finite intersection property, obviously, but the intersection of all of the things is empty. So the open interval is not compact. Okay.
Anna,
Yes.
did you say example 4 is really example 3 in disguise?
Well, I said that the example 4 is example 3 together with example 1 in disguise, because example 3 was the use of Tikhonov's theorem, saying that if I have a compact space to any power, then it's compact. So now I'm using it for 1 being finite. So if I say that 3 is examples of applications of Tikhonov's theorem, then they are the same category of examples.
Okay.
So not the same in the way that they would be the same, the Tikhonov cube 0, 1 to kappa contains the Cantor cube, of course, because it is universal for all compact spaces of that weight, but not vice versa. Okay, so now let's prove that beta n is a compact space, and I introduce this equivalent notion of compactness for a reason, because it's the one that is easy to prove for beta n. So suppose that we have a family of closed subsets with the finite intersection property, and then we know that this closed family really corresponds to filters, right? We have that each of these C alpha is really an intersection of some A alpha J, right? Hat where we have that J is from some indexing set, right? So it's an intersection of the basic open neighborhoods. So I take these corresponding filters, and then if I take into consideration the finite intersection property, that means that if I take finitely many of these filters and I take a union of them, then this is going to generate a filter. It's going to have as a filter the finite intersection property, and therefore if I close upwards for supersets, then this is going to be a filter, right? Because it's going to be the filter that corresponds to the intersections of these C alphas for alpha in F. Then, well, let's suppose that, however, we do not have that the intersection of all of these C alphas contains anything, which means that if I look at the union of all of these filters, then this is not going to generate a filter. Well, what does that mean? That means that there is going to be some elements in the filters that are incompatible to give you a filter. That means that there is going to be some finitely many things. We can think that they are coming from different FC alphas, because from the same we could just take intersection that has to be in FC alpha. So I can take some finite subset and I can have that A alphas are in FC alpha is empty, right? Meaning if I want to generate a filter, I have to take finite intersections and supersets. So what if I do not, what if finite intersection gives me something that is not allowed? Well, but this contradicts the finite intersection property, because we said that if we take finitely many of them, then by finite intersection property of C alphas, we have that this union has also the finite intersection property. So this is not possible. Okay, so this union is a filter, and then we can extend this to an ultrafilter by the axiom of choice. And then this ultrafilter is going to be in this C alpha. Actually, already the filter generated by this is going to be the intersection. So it doesn't necessarily have to be one element. Any ultrafilter extending that is going to be the in the ultrafilter in the intersection. Any questions? Right, let me maybe write down here on the sides just what we have been using. If I have two closed sets in beta n, then the intersection of CD, this corresponds to the filter that is the union of the filter corresponding to C and D respectively. And this is the way that we sometimes say that we generate a filter. That means that we take the smallest filter that contains both of these filters, right? So of course this union itself doesn't have to be a filter, but if we take pairwise intersections, then this is going to be a filter as long as C intersection D is non-empty, which is guaranteed by the finite intersection property. And then it's going to correspond to this. Now, if I have finitely many of them, then I might have to consider intersections of more things, right? So we said that filter only has to be close under intersection of two things, but well, let's say three things, then the first two have to intersect, right? And then this gives me something, and then I take the third one that has to be in the ultrafilter. And then I had a third one, and I apply the second condition on a filter to the intersection and to the third set, right? So in the end, I get that the intersection of A1 to and A3 has to be in the filter, right? So B. The second condition about being closed under intersections of two sets is really being closed under intersection of finitely many sets. Okay, so now, as I said, beta n is large in many ways. It has many, many points, right? We know that it has two Aleph not many points. And it is non-metrizable. And there's many ways to prove that. But this one just says something nice about the non-principal ultrafilter. So we are going to go through this one. So for a topological space to be metrizable means that the topology, the open sets, they come from some metric. That means that there is a metric on the points of X that induces the topology. So if I look at the epsilon open balls around points, then with respect to this metric, this is going to generate the same topology as the original topology. There can be different metrics that generate the same topology, but they will be non-trivially related. So every metrizable space has to be first countable, and recall that a space is first countable if every point has a local basis that is countable. So if I have a point, then I can find countably many neighborhoods, and without loss of generality, they can be decreasing, such that if I have any neighborhood, right, that contains it, then there exists an n such that On is in V. And it has to be at every point. So now we show that actually any non-principal ultrafilter has uncountable bases. So of course, if I take a principal ultrafilter, then I can just take the set, bar X. If I have principal ultrafilter given by X, then bar X is going to be all ultrafilters that contain X. But this is only one thing, right? Only UX satisfies that. So every principal ultrafilter is an open set. It's an isolated point. So it itself is a local basis for itself. So they are definitely very much points of first countability, but not every element of beta n is, and any non-principal ultrafilter actually is not. So suppose that we do have a countable basis. So if I have a basis consisting of open sets, we said that it's something that is going to give me an open set within any open neighborhood of that point. So we can as well think that they're the basic open sets, because those are smaller. They generate every open set is a union of these. So I can think that they are all of the basic form. That means some AI subset of n giving me this AI bar. And these AIs are in U, which is the same thing as saying that U has AI bar as a neighborhood. Okay, so now from that construction of these B alphas in the existence of P point, we already know that there is going to be something that's almost below. We can construct that point by point. Because we are looking only at a countable basis. And then this is easy to verify, that if we are in the non-principal ultrafilters, then the finite is negligible. So if I have ultrafilters containing B, and I compare it to the ultrafilters containing C, and B is almost included in C, then this is a proper containment. Whatever is sticking out of B would only give me non-principal ultrafilters, and those are not considered inside of here, right? So now, when I look at this, I get that this A bar is going to be a proper subset of the intersection of all of these AI bar. And this is an open set. So I get that there is some open set that is below every neighborhood that I have chosen for my local basis, and therefore this is not this was not a local basis because I have nothing to put from my basis below this a bar, right? So this contradicts that this was a basis. Actually, if I had such a non-principal ultrafilter, then I would get immediately that it is a p point. But we know that they don't exist. So there's many ways to prove this. But this says actually that this is true in ZFC. So it is not possible to have a model in which you would have an unprincipled ultrafilter with an uncountable basis. Any questions? Okay, so there is a way to describe what beta n is without saying anything about ultrafilters. And that is, and then we can show that it is actually a space that satisfies this property. So this is in a way a completely topological characterization, and it's one of the ways that the Chicstone compactification came to exist. And it's about extensions of functions, right? We are often interested in when we can extend a continuous functions to a larger domain, and often we cannot. So when we can, we are very happy. So here, the Chicstone compactification is something that makes it always possible. So what is the scenario? I start with my natural numbers, right? The natural numbers, they are embedded inside of beta n as principal ultrafilters, right? So this I is that identification of natural number with its principal ultrafilter. And whenever I have a function that's defined on natural numbers and goes into compact space K, so here natural numbers are discrete, so we don't really have to talk about continuity at this point, but I can extend this function to a continuous function from the Chicstone compactification to K, meaning that if I identify the natural numbers with the principal ultrafilters, then on those, the extension is going to behave the same way as my original function. Okay, so we have that, let me maybe draw a diagram. We have the inclusion from natural numbers into beta n, and then any function from n to k, k is compact, there exists an extension, continuous one. So let's verify that beta n as we described. So this thing, okay, I call it beta n, but we don't know yet that beta n actually satisfies this property. And we can actually show that this property uniquely defines this space up to homeomorphism. So if we show that beta n satisfies that as a space of ultrafilters, then it is really a definition because that such a space is unique. Okay, so let's start with some function, and let's look at an ultrafilter, and we want to extend this function. We want to extend this function to take some value on the ultrafilter. So how does a function from n into k look like? Well, we can just think about that function to be, to be a sequence of points in K, right? F of n is some Kn. So that's another way to think about the function, just as a sequence. And now for any u in the ultrafilter, right? This is an ultrafilter of natural numbers. So it chooses which set of these Kn's it thinks is large. So let's say that this is going to be, the indices are going to be in U, right? So this is some f of U, where U is an element of the ultrafilter. And I take a closure in there. So this corresponds to taking this subset of natural numbers, right, U, and looking at U bar, and then we would like that this CU to be the image of this U bar in beta n under the extended function. So we are going to look at these closures. Well, these are some compact subsets of K because closed subset of K is compact. And because U is a filter, then if I look at finitely many of these UIs, right, U1 up to UN from U, then the corresponding CUs, they need to have a non-empty intersection. CUI, right, because this has to contain the closure of C of U1 up to UN, and this is non-empty, right? So so this intersection is non-empty. So this CU has a finite intersection property, and because K is compact, we know that all of the intersection is going to be non-empty, and one can verify quite easily that because U is an ultrafilter, then this set is just a singleton. It cannot be two things because for any two things we could find some ultrafilter, some set in the ultrafilter that is going to separate them. Any questions? So in general, this is a notion that we will be also using next time. This element f tilde of U is what we call the U limit of the sequence K n, right? Which these are just f of n under my function. So ultrafilter limits, they always exist. Whereas if I look at limits in the usual sense where we want the indices to lie inside of the Fresher filter, we might not succeed, right? Unless K is compact, we do not have, I mean, unless K is metrizable, we do not necessarily have a sequential compactness. Any questions? Okay, so this is a universal property that has many ways of, many phases, but in category theory, there is a unified way to say that, and it tells us about an existence of an object of a special form that we somehow know how to deal with, and the compactness is what we are mostly interested in, to which we can extend every function. Okay, so now we can transform anything that we said about ultrafilters into talking about in the topological setting. And we talked about p-points. So let's see what a p-point means in the topological setting. So let's recall that an ultrafilter is a p-point if whenever I have a countable collection of sets, then there is going to be a pseudo intersection that is inside of the ultrafilter. So when we translate that, right, then we have that each of these AI, they are in U. So that means that the AI bars are open neighborhoods of U. So we can think that if I have any sequence of open sets, then I can think about them as being these open basic sets. And then when I have the pseudo intersection, because we have that in non-principal ultrafilters, that if A is almost included in B, then the closure in the non-principal ultrafilters is contained in the closure of B. So I get that when I look at these open neighborhoods, then the pseudo intersection is going to be below all of them. Okay, so these are, and this p-ness that also has taken off on its own in topological spaces. So whenever you have some property that says that if you have countably many neighborhoods of something point subspace, and then you have a smaller neighborhood inside, and usually there is a p in front of it, right? So if I have countably many neighborhoods, then there is going to be some neighborhood that's below all of them. Okay, any questions? Okay, so this is what we did for today. Because we have some time, one thing that I could do today is to tell you why the axiom of choice and Zorn's lemma are equivalent. Would you like to see that, or are you too tired? I think it's very, very late for you, isn't it?
I would like to see it.
Okay, sounds good. So, you
Sure.
know, yeah, you guys do not have the camera on, so that makes it easy for you to go to sleep if you need to, right? So let's do it that way. Okay, so I always forget, you know, one advantage of having been in person, disadvantage, I guess now, is that I totally forgot how to use this. So I know that you can add a page to this.
Is it paper? No?
Yeah, but it's not like giving me, where do I, no, this is not, see?
What about that plus sign next to
Yeah,
that?
but that's like, so photo library gives stickies. I did it very recently and I figured it out. So let me see, that must be a good way. No.
Maybe you have to go to the last page.
Yeah,
And-
but I think that's not the case because you can add a page
Oh.
whenever you want. Let me see, is
Mhm.
there any? Think no, I'm so sorry. This is funny. It was funny how quickly we, maybe if I do this, how quickly we got used to using Zoom, and also how quickly we forgot it. Come on,
Yeah.
this must be the way, no? Like this is not possible. That you want to search. Okay, I can just open a new document, and then we can, right?
Yeah.
That must be easy here. Nope. Here. Ah, there we go. So we have on one side, we have axiom of choice, which tells us that if I have any family, non-empty family of non-empty sets, then I have a selector function such that f of any. So let me distinguish maybe these s's by writing differently. It's easier when f of s is in s. This s. Okay, and now we have the Zorn's lemma. Right, that says that if I have any partially ordered set and every chain has an upper bound, then P has a maximal element. Okay, so let's go first in this direction where Zorn's lemma implies the axiom of choice. Anybody has an idea of what poset we could consider? So this is a standard thing, and you might have seen it in the first thing that I believe you have been introduced to a little bit to, is that when we want some object, which in this case is the selector, we try to approximate it, right? We try to find some way to eventually get to it. So this poset is going to be of finite, partial functions from S to the union of S that are partial selectors, right? So these are all partial selectors from S to union of S. What does it mean partial? It means that you're not necessarily looking on all of S, you're looking at some subset. And we know that for a finite set, this is true. So this is a non-empty poset, right? So for instance, if I choose just one S in S, then I can look at this partial function. This is going to be an element that goes just from the single element subset of the collection into the union of the collection, which is S itself. So it's just going to assign to S anything in S. And we said that all of them are non-empty. So there is something in there, right? So we know that definitely this is a non-empty partial order. And now we want to verify that every chain has an upper bound. So let's suppose that we have a chain PI from some index set. Right, so this is some I is linearly ordered, That means that it doesn't have to be natural numbers. It can be, of course, something a lot larger, but it's some linear order. So it means that pi is as a function, right? Function is ordered pairs, so it's a set. Pi is smaller than pj, so it means that pj is a set that takes into account more elements of my collection S whenever I in the linear order is less or equal than j. So I have a chain. What would be a candidate of an upper bound of such a chain? Really the same thing as we did for the extension of ultrafilters.
The union.
The union, excellent. So always try that, right? So if this is my C, union of C. Well, this is going to be a function, because if it were not a function, then this is a finite array condition. It would have been witnessed on some previous thing, and it's still going to be a selector because this is a pointwise definition. So this is going to be inside of P. And now what remains to show? Well, so because we have an upper bound, we have a maximal element, right? So let some m in P be maximal. We want to show that the domain of M is all of S. Right, so this is actually going to be a total function. And then we are done because this is exactly what a selector is. So why is it total? Well, suppose it's not, so it's not defined somewhere, right? Suppose there exists S in the collection without the domain. What's going to happen? Well, we will be able to extend, and then we are going to break the maximality. Well, if I have just one S, I can just define the value on it, right? So I have the function M, which is a partial selector on its domain, and I can just take this union, the ordered pair where S chooses any element from S. Well, I can choose for every one element set something out of it, and M has already chosen it from its domain. So this is going to be a strictly bigger function than M, and that contradicts maximality, right? And this is still in P. So you see, it's actually very simple.
Sorry, you mean the set containing the ordered pair S, S?
Okay. Thank you. Yes. All right. So we got this direction.
Right. Before you go to the other direction, can you, go back to, you have the partial, right? We're trying to prove that Zorn's lemma applies AC.
Yes.
And there is this analogy where you did in the, I think, the third line where you have a little p going from that one. Why does this not apply to the entire family? So why does it work for finite sets only, but not the entire family? I think that would be the distinction to talk about, right?
Right. So yeah, there is instances where it's possible when you can somehow define the function. So when the function is definable, say that you have a well order in which you are choosing the things, and you're saying I'm going to choose a minimal thing among some things. So this is a definability thing. So but unless you have such a thing, let me think. I haven't taught set theory in a while. What would be the easiest example where it is obviously, where you can show easily that you do not have a selector unless you choose one. Let me see. Right, the thing is that so what is the issue here, right? So what you need in the F, you are constructing a set. Every axiom that you have looked in the previous lectures tells you this is a recipe to construct a new set out of previously constructed sets, right? So the point of axiom of choice is that you would have to have, if it were provable in ZF, then some of the axioms would somehow give you that given this set, so this set exists because it's given to you. This set exists because you have the union axiom, right? So that's fine. Now, what you want is to separate another function. So this f, this is a set, which is a subset of S cross the union S. This exists again, right? Because we can do Cartesian products out of the pairing axiom. So this is fine. But when we are looking at separating a set, then there has to be a formula. And there is not necessarily a formula always for every selector. And I would have to think a little bit, but I'm even thinking that if I were looking at power set of X, and then if you look at the union of power set of X, which is just equal to X, then what this selector does, it picks from every element, so from every subset of X, one representative, right? It decides this is the representative, but we do not necessarily have anything that tells us that this is going to be the case. Okay, I think that, yeah, so it's, I would have to give you a specific example, right? If you, for instance, have natural numbers here, then this is not gonna be the case because for every set, you have a minimal element, so you can make that choice. There, however, equivalence relations, so what basically the selector does is, you have a collection of sets. So let's say that you have a partition of a space, so you have some equivalence relation, and you're looking at getting a representative of every class, and this is something that definitely.
Yeah, I mean, but why is it that when you have that little p, when you have a family of just one single set, there is no issue with this?
Right, because so one might, why is there no issue? I had a condition, right, which I didn't write down here, and that is that they are non-empty, right? So for every S in S is not equal to the empty set. What does that mean? That means that there exists some X such that X is in S. Right. So now this X, right, I can instantiate. So then this element exists. So I can just pick an arbitrary element, right? So then I can say let X be in S and let F be equal to just this one thing, SX. And this I can do because S is a set, X is a set, and ordered pair I can do by pairing axiom, and then the singleton set I can again do by pairing axiom. So and then you can exist. You can do this for every finite
exactly function, and then you take the union, right? And then you have this element.
But I cannot do that necessarily simultaneously for an infinite connection, right? That's the thing that.
Yep.
Thank you. Yeah, I should have an example at hand, but I have to refresh. That's your homework, Jake, for next time to give me a simple example.
Yeah, a good one for him.
Exactly, we are just learning these things, so yeah, this is basics. So I have a few minutes to give you a hint at the other direction so that we know. I think that the easiest is if I delete this, because then we see the statements, right? It's always the hardest when on slides they're trying to prove something that was on the previous slide and you forgot what was the thing that you were trying to prove. Happens all the time though. So we have that AC implies Zorn's lemma. So I start with an arbitrary partially ordered set, and I want to somehow build my S and a selector that is going to be useful for me to show Zorn's lemma, right? So there is different proofs, of course, as it always goes with these things that are very important. So one proof is by contradiction. So we are going to have a poset such that every chain has an upper bound. But P doesn't have any maximal element. Well, what does it mean not to have an maximal element? It means that whatever element I choose, there are going to be things in my poset above it. So for every P in P, let XP be all those Y's in P, oh, sorry, the big P, such that P is less than Y. Right, so this is a collection of sets. And therefore I have a selector. So I can look at F that goes from the sets XP, from P in P, into their reunion, which is some subset of P. And so it takes any of these XPs and assigns to it something inside of XP. So now, because I have these indexed by P, I can identify f of x of P with P. Then I get a function such that f of P, this is something inside of the XP. Therefore, this is greater, strictly greater in the partial order P than P. So now I can do transfinite induction or recursion, and I can define a function from ordinals into P that is going to be injective, right? So I can choose some P, arbitrary P, and I'm going to say that 0 maps to this P, and then 1 is going to map to this f of P, right? Which is now strictly greater than P. Therefore, they are not equal. And then, of course, 2 is going to map to f of P, f square of P. And then I can keep going, and omega is going to be an upper bound, which exists by my assumption of all of these f to n p's for n in omega, right? And then I can continue. F omega plus 1 is going to be, well, let's say that this is g of omega, and then f apply to that, and I can keep going for all ordinals, because at limit stages I always use the upper bound, and at successor stages I always use an application of f, and all of these are going to be different, and therefore I get an injective function from the class of ordinals into the set of P, and this is not possible. Class is way too big, and I have that an image of a proper class is going to be a class and therefore not a set, and this is a contradiction. Any question? Okay, thank you, Michael, for being here. Okay, yeah, so this is it. I'm glad that we got to do this. It actually made sense to include it today, so that's great.
Okay, thank you, Dana. It was a very interesting topic to talk about. And thanks for all of you who attend. And I'll see you guys again in this set theory. That will be on Wednesday, right?
That's Wednesday morning, right, for you? Mm-hmm.
Wednesday morning, yes. So the next session will be on recursion theory. That will be 12 hours from now. So I'll see all of you again in 12 hours. For those of you who need to take a rest, it's time for you to sleep, I guess. And I'll see you again. And thank you once again, Dana. I'll see you again on Wednesday.
My pleasure. Yeah.
Bye,
Enjoy,
everyone.
guys. Bye.
Bye.